Okay, so good morning, everyone. So my name is Huadong Mort from UNSW Canberra School of Engineering and Information Technology. It is our honor to invite Professor Gardoni from UIUC, and Professor Gardoni is the professor in the Department of Civil and Environment Engineering and he is also the editor-in-chief in the Journal of Reliability Engineering and System Safety and the founder and the former editor-in-chief of the journal Sustainable and Resilient Infrastructure. His research interests include probability mechanics, reliability risks, and life cycle analysis, decision making under an uncertainty for critical infrastructure. Professor Gardoni is the 2021 recipient of the Alfred N. Award on the Risk Analysis and Management of Civil Infrastructure from the American Society of Civil Engineers for his contribution to risk reliability and risk analysis and his leadership in these fields. And today, Professor Gardoni will give a presentation on an overview of regional risk and resilient analysis. And in this work, he will give a introduction. He will give an overview of the how to conduct a regional risk and resilient analysis considering multiple hazards and different infrastructures, as well as the effects of deterioration and interdependencies among infrastructure. Finally, the presentation concludes with the modeling of business interruption due to a hypothetical earthquake in the new Madrid zone. And let's start the presentation for Professor Gardoni.
I'm Paolo Gardoni. I'm a professor in the Granger College of Engineering at the University of Illinois at Urbana-Champaign. I will present an overview of regional risk and resilience analysis. As a background, natural hazards can have devastating impacts on communities, and losses depend on the characteristics of the hazards as well as of the structures and infrastructure in the affected region. Mathematical models of hazards, damage, and impact are needed to minimize the consequences of future events. The general philosophical approach or modeling principles in developing all the models presented today is that models need to be sufficiently accurate to provide the information of interest, general, and transportable. They need to account for all relevant information, including our understanding of the physics and mechanics of the phenomena and available data. They need to be probabilistic and account for the relevant uncertainties, and they should not be unnecessarily complex. And the proper granularity of networks and modular resolution need to be defined carefully. Empirical models that do not account for our understanding of the physics are generally less accurate, less general, and less transportable. Models that are unnecessarily complex might have high computational cost, have unnecessary levels of data requirements, and introduce significant uncertainties. Today I will present a roadmap for regional risk and resilience analysis. I will also introduce the concept of resilience as one of the most currently desirable characteristics of structures, infrastructure, and communities, and also as a necessary information for risk evaluation and decision making. While deliberately focusing on the bigger picture, I will mention some specific models and formulations that we develop for regional risk and resilience analysis. I will highlight how we follow the modeling principles in the previous slide, and I will provide references for additional details. This is the outline of today's presentation. I will start by talking about regional risk analysis. Then I will talk about regional resilience analysis, and then about uncertainty quantification and model validation. And finally, I will conclude my presentation with a few remarks and mentioning a few additional resources. So let's start by talking about how to predict the physical damage. There are three fundamental steps to predict the physical damage. We need to model the hazard, we need to characterize structures and infrastructure, and finally, we are ready to predict the damage. So in terms of modeling the hazards, communities might be subject to multiple hazards, like flood, earthquake, tornado, and wildfires, just to mention a few. Accurate hazard modeling requires accounting for the temporal aspects of the hazard. For example, for the seismic hazard, sequences of main shocks and aftershocks all contribute to the overall damage. And for weather-related hazards, climate change is impacting the likelihood of occurrence and magnitude of extreme events. So as to the seismic hazard, we develop a two-step method to generate synthetic main shock aftershock ground motion sequences that are consistent with the site characteristics. In addition, accurate hazard modeling also requires accounting for the spatial variability of the hazard. Several factors limit the accuracy of the traditional ground motion prediction equations commonly used in seismic hazard analysis. So we develop high-resolution, three-dimensional physics-based models that account for these near-field effects. To illustrate some of the concepts presented today, I will use Shelby County, Tennessee. We have been considering a number of test beds that allow us to test and verify different algorithms through calculations, experience, and engineering judgment. One of the test beds is Shelby County, Tennessee, that has a total population of about 1 million people and could be subject to earthquake scenarios originating from the New Madrid seismic zone. We propagated an hypothetical earthquake with magnitude 7.7 and an hypocenter at a depth of 14 kilometers with two different levels of resolution: a high-resolution model in the near field and a low-resolution model in the far field. Other hazards where we model the propagation in space and time using the same modeling principles are wildfires, and we also model the propagation in space and time of storm surge associated to tropical storms, again using the same modeling principles. The next step is to characterize the structures and infrastructure. Communities are composed by multiple layers of structures and infrastructure, including buildings, transportation network, electric power network, and water network. Each network then consists of a number of different elements, and for example, in the water network, there are elements that serve the following 5 key functions: supply, transmission, treatment, pumping, and storage of water. And the elements can be divided into linear elements like pipelines, tunnels, and canals, and point or nodal elements like tanks and reservoir. For a given region of interest, we also need to define the footprint of each network that we need to model. The footprint of each network might exceed the footprint of the region of interest. Different networks might have different footprints, and the definition of the footprint of each network typically depends on 4 key factors: the type of information of interest, whether it's physical damage or loss of functionality, the existence of easily recognizable physical boundaries and the possibility to model the boundary conditions, The existence and location of strategic elements that need to be included, like generation nodes, and the modeling of the damage propagation among infrastructure systems. For the example of Shelby County, the water network is modeled at the county level because this is a self-sufficient system, while for the electric power network, we model the entire state of Tennessee in order to be able to run a power flow analysis. Once we define the footprint of a network, we then need to define its granularity. We define a tributary area as the area served by a single network node. And then by changing the tributary area, we can define networks with different levels of granularity. And in the limit, the most refined model considers each single parcel or house lot as the tributary area. The nodal value of the quantity of interest is then the spatial average over the tributary area. And in terms of modeling, different granularities affect our ability to describe the spatial variability of the impact over the area of interest, affect our ability to describe the changes in the network capacities and demands following a disrupting event, and affect our ability to describe the recovery process, since skeletonized networks only include main lines and not the smaller distribution lines. It is important to capture the spatial variability of the impact over the area of interest because certain population groups might be more impacted than others or recover more slowly, and tributary areas that are too large would underestimate the actual societal impact. For the example of Shelby County, we modeled the potable water network with two different levels of granularity. We consider a skeletonized model of the network that I'm showing here on the left that only considers the main distribution lines. We also develop a detailed model of the network where we consider every line going to every individual home. We model the electric power network with two different levels of granularity based on the area of interest. We develop a detailed model for the power network of Shelby County to capture the variability of the impact within the county. And we model a skeletonized network outside of Shelby County, which is sufficient to perform accurate power flow analysis. We also model the transportation network for Shelby County, and we consider a detailed model for the roads to estimate the impact on the general mobility of individuals and to capture the access to essential facilities such as hospitals and police stations. Going beyond this example, we develop a mathematical formulation to systematically select the appropriate network granularity. We start from a coarse granularity and then increase it until we reach a desired trade-off among accuracy, simplicity, and computational efficiency. To define the trade-off, we develop novel metrics that measure the level of agreement between estimates of the quantities of interest computed using different levels of granularity. When limited information on the networks is available, we construct networks by combining the limited available information with engineering principles and standard practice. For cases when no information is available on the network topology and functional properties, we develop a formulation to construct realistic, functionally equivalent networks using other geospatial and non-geospatial information. Finally, we can predict the damage. For the point elements such as buildings, bridges, distribution nodes, we use fragility curves, which are defined as the conditional probability of attaining or exceeding a prescribed performance level for a given intensity measure at the site. For the linear elements, such as roads, pipelines, electric power distribution lines, we use repair rate curves, that provide a number of expected repairs per unit length of the linear element as a function of the intensity measured at the site. We develop physics-based fragility functions for the nodal elements. To formulate physics-based fragility functions, we develop probabilistic capacity and demand models based on the rules of physics and mechanics and information from the field and the laboratory. This is the general expression for the probabilistic capacity and demand models. Yk on the left-hand side is the physical quantity of interest. X are basic capacity and demand variables that are provided as inputs. Theta is a vector of unknown model parameters. T is a variance stabilizing transformation, and I will explain in a few seconds why we typically need to use it. As we move to the right-hand side of the equal sign, Y hat is a deterministic model that is constructed based on the rules of physics and mechanics. Gamma is a correction term that is also based on rules of physics and mechanics, but is also calibrated using the information from the field and the laboratory. Anything that is not captured in the first two terms, Y hat and gamma, goes in the additive model error, where sigma is a standard deviation which is assumed to be independent of x, which is the homoscedasticity assumption, and epsilon is a random variable assumed to follow the normal distribution, also known as the normality assumption. The three assumptions, additivity of the model error, homoscedasticity, and normality, in general are not satisfied in the original space. And this is why we often need to use a variance stabilizing transformation so that in the transform space, these three assumptions are at least approximately satisfied. Using the probabilistic capacity and demand models, we can obtain fragility estimates by conducting a rigorous reliability analysis. In doing the reliability analysis, we can also account for the uncertainties in the model parameters theta, and we have three options. We can construct point estimates where we deliberately ignore the uncertainties in the parameters theta, and we simply use the posterior mean of the thetas or their maximum likelihood estimates. We can also construct predictive estimates of the fragilities, and here we are including the uncertainties in the parameters theta by taking the expected value of the fragilities over the space of the unknown parameters theta. In this case, we are blending together all sources of uncertainty. To keep the epistemic uncertainty that comes from the theta separate from the other sources of uncertainty, we can also construct confidence bounds, which we typically do on the reliability index first and then convert into bounds on the probability. The physics-based fragility functions have 5 important advantages. First of all, the fragility functions are parametric. So once the capacity and demand models have been calibrated, they can be used to assess the fragility of other elements with characteristics that fall within the range of the data used in the calibration. Second, the modeling can be done at the structural components level, which can take advantage of the experimental data often available for structural components and not full systems. The fragility estimates are obtained from a rigorous reliability analysis rather than by making simplifying assumptions on the shape of the fragility functions, such as assuming a log-normal cumulative distribution function. The parametric formulation allows us to easily incorporate the effects of deterioration, as I will show later in the presentation, as well as information from non-destructive testing and structural health monitoring. And finally, the estimates account for the relevant uncertainties, including statistical uncertainty that comes from the scarcity of the data for the model calibration, and model uncertainty due to the simplifications in the mathematical model. Going back to the example of Shelby County, we use the earthquake intensity measures and fragility functions to estimate the damage of each individual building in the region. On the top row, I'm showing the estimated damage using a traditional attenuation relationship. On the left, I'm showing the most likely damage for the residential buildings. In the center, the most likely damage for the commercial buildings, and on the right, the most likely damage for the industrial buildings. In the second row, I'm showing the most likely damage state, which is now estimated using the more sophisticated 3D physics-based model of the hazard. We observe localized high damage due to the hazard amplifications in certain areas, which is not captured by the traditional attenuation relationship. And also, we observe on average less structural damage in the residential buildings, but more structural damage in the industrial buildings given their specific location. We use this formulation and modeling principles also to develop physics-based repair rate curves for the linear elements like pipelines. Current repair rate curves are generally based only on statistical inference and have significant uncertainty. The developed repair rate curves are able to account for the physics and mechanics of the problem, are able to account for the properties of the soil where the pipelines are buried, and are able to separate for the damage at the joints from the damage at the segments. The infrastructure suffer from aging and deterioration over time, and aging and deterioration might considerably reduce the service life and reliability of infrastructure. Aging and deterioration are also becoming a growing problem for all types of infrastructure in the US and around the world, and they are making damage data from past events, when there was less deterioration, less informative. Infrastructure might be subject to multiple deterioration mechanisms that could be gradual, like corrosion, or due to shocks, like past earthquake events. Changes in the state variables, like material and geometry, can then lead to higher vulnerability to hazards, higher fragility curves, higher repair rates, and higher probabilities of failure or reduction in functionality. There can also be interactions among different deterioration mechanisms that can accelerate the overall deterioration process. However, formulations available in the literature do not take into account the possible interactions between different mechanisms. So we develop a state-dependent formulation to model the deterioration accounting for these interactions. The deterioration of the state variable x are modeled as a function of the external conditions, which we call z, and their current state. And then changes in x lead to changes in the capacity of the system, as well as in the demand on the system. And the updated capacity and demand models can then be used to estimate the time-variant probability of failure. The gradual and shock deterioration can be modeled consistently using stochastic differential equations. The choice of the driving noise affects the behavior of the process, and semi-martingale driving noise can be used to combine gradual processes in the form of Brownian motions and shock processes in the form of compound Poisson processes. For example, considering a reinforced concrete bridge in a transportation network subject to corrosion and seismic load, the occurrence of seismic shocks accelerates the corrosion rate, and results show that considering the interaction of the two deterioration processes considerably affect the lateral stiffness, leading to significant changes in the fragility. Similarly, we use this formulation to obtain time-varying repair rate curves for linear elements like pipelines. The results show an increased vulnerability of older pipes, whereas the empirical repair rates available from the literature do not change with time. In addition to temporal, there are also spatial variability in the state variable x and the external condition z. So we develop an improved latent space approach for modeling non-stationary special temporal random fields using physics-based regressors. A special temporal random field V is the collection of random variables at different spatial locations S and time t, and a non-stationarity means that the properties of V vary in space and time. So the proposed formulation considers different regressors as latent dimensions and then model the statistics of the random field as a function of these latent dimensions. The proposed formulation allows us to include the influence of physical regressors with a clear physical meaning in the definition of the random field. We then couple the state-dependent formulation for deterioration with the formulation of non-stationary special temporal random fields to model the effect of deterioration on the state variable x, accounting for their spatial variability. All of this is done at the material scale. And then by modeling the section and element properties as a function of the state variable x, we can obtain random fields at higher scales that can then be integrated in the network models. Next, I want to talk about connectivity, functionality, and interdependencies. The connectivity of infrastructure depends on the physical damage to the individual components and the original network topology. The connectivity of individual elements in the network describes the network topology, and the network can be represented, for example, using an adjacency matrix, which is a matrix of ones and zeros, where 1 indicated there is a direct link between two nodes and a 0 indicated there is no such a link. Different measures can then be used to quantify the network connectivity both before and after a disrupting event. Examples of such measures are the diameter and the efficiency. The adjacency matrix can also be used to convert the physical damage to the components into the impact on the network flow. For example, considering a water network, the adjacency matrix can be used in a water flow analysis that defines the network capacity, accounting for the physical damage of the individual components as well as the network topology. Capacity of the water network here refers to its ability to deliver a certain amount of water of minimum quality and at the minimum pressure. Physical infrastructure often depend on each other, and such dependencies might indirectly affect a network capacity. For example, buildings need the service provided by the water and power networks. The water network depends on the power network because it needs power at the pumping stations and control systems. And as a result, even if a network has no physical damage, there could be a loss or reduction of functionality of such network because of the physical damage and the corresponding loss of functionality of a supporting network. So we need to translate the physical damage into a loss or reduction in functionality and then propagate such loss or reduction across all dependent networks. Several classifications of interdependency are available in the literature. While such classifications are helpful to qualitatively describe the relations among networks, they are not helpful in the mathematical modeling of interdependencies. We developed an orthogonal classification of network interdependencies. The proposed classification supports the mathematical modeling of network interdependencies. Using the proposed classification, we capture the relations among several classes rather than simply listing them. The interdependency between two networks can be represented expanding the adjacency matrix. What I'm showing here is an example expanded adjacency matrix for two networks, A and B. However, an expanded adjacency matrix cannot be used for complex networks, and for example, for networks with many nodes and multiple interdependencies. Alternatively, using the proposed classification, we can define interface functions to model the network interdependencies. The interface functions modify the defining characteristics of networks to include the effects of interdependencies. And the formulation can be used for very complex networks. And for example, considering the water network, we can model the change in the capacity of the water network due to both the direct damage to the network and the damage to the supporting electric power network. Considering the example of Shelby County, we first estimated the impact of the hypothetical earthquake on the power network capacity, and we estimated a complete power blackout for Shelby County. Then we estimated the impact of the earthquake on the water network capacity. First, without considering the dependency of the water network on the power network. And then we also consider the dependency of the water network on the power network. And we see that accounting for such dependency significantly reduces the ability of the water network to deliver water. The service provided by the supporting infrastructure affects the building functionality. As an example, we estimated the probability that each commercial building is not functional considering structural damage as well as access to water and power. Considering only the structural damage, we significantly underestimate the lack of functionality of buildings, and I'm showing here on the left. In this example, due to the likely power blackout in Shelby County, in the immediate aftermath of the earthquake, the most likely functionality state of the buildings is non-functional, which I'm showing here on the right. Not only the capacity of a network, also the demand on the network can be affected by dependencies. For example, building damage can lead to people dislocation and business interruption, which I will discuss more later, that affect the post-event water network demand. So the updated network capacity and demand can then be used in a flow-based network analysis to assess the functionality and reliability of the network. Considering Shelby County, we studied the effects on the water demand of people dislocation due to a seismic event. People dislocation is estimated using a logistic model based on a probability mass function of the residential structural damage and other socioeconomic factors. External people dislocation results in a decrease in the water demand at the node of the water network, and the assessed physical damage to the water network and the reduced demand due to people dislocation are then used in a water flow analysis to see if the new water demand is met. And we see that thanks to the reduction in the water demand, the water network performs better than if we did not consider people dislocation. To deliver the intended service, a building needs to be both functional, as discussed earlier, and also accessible. So in addition to looking at building damage and water and power availability, we estimated the impact of the earthquake on the transportation connectivity. The damage to bridges, in light of the specific network topology, results in a significant impact on the connectivity, and such impact is not uniform over the region of interest. In addition to bridge damage, falling debris from damaged buildings is another factor affecting the transportation connectivity following earthquakes. So we estimated the likelihood of road blockage due to debris by developing a physics-based probabilistic model using a formulation consistent with the one introduced earlier for the capacity, demand, and repair rate models. The information on accessibility can also be used to develop optimal policies and community planning. For example, we develop a formulation to optimize land use planning for seismic risk mitigation, finding a trade-off between post-earthquake accessibility and housing requirements. Carrying out flow analysis can be computationally expensive, especially when the analyses are part of an optimization. So we developed a new physics-based approach called functional connectivity analysis, or FCA, to obtain information comparable to flow analysis, but at a fraction of the computational cost. Next, I will talk about how we can predict the likelihood of business interruption. Business interruption is a disruption of the normal operations of a firm. And we can classify business interruptions into two types: ordinary business interruption, which is due to the physical damage to plants and facilities or the equipment, and contingent business interruption, which is due to the dependency of business operations on the supporting infrastructure, inflow or outflow of goods, and employees and customers availability. Only considering ordinary business interruption significantly underestimates the likelihood of business interruption. When we consider the damage to the supporting infrastructure, the likelihood of business interruption can be significantly higher. We developed a ground-up approach to estimate the likelihood and duration of contingent business interruption. The approach incorporates the dependency of business operations on the functionality of physical structures, infrastructure, and social systems. For example, power and water flow analysis tell us if businesses have access to the services needed to run their activities. Similarly, the modeling of the transportation network allows us to capture the ability to deliver and transport products and supplies, and allow us to capture the employee's ability to go to work if they are available. An employee, in fact, might not be available either because he or she is a casualty or because he or she has to dislocate. We estimate the probability of the severity of a casualty and the probability of dislocation as a function of the structural damage to residential buildings and socioeconomic characteristics. As an example, we predicted the business interruption of an hypothetical shipping company in Shelby County, Tennessee. To predict the probability of business interruption, we consider the structural damage as well as lack of water and power. We see that the loss of service from the supporting infrastructure can have a significant impact on the probability of business interruption. Next, I want to move on and talk about regional resilience analysis. Current design approaches are pushing toward options that are resilient under different exposure conditions. We want to increase the robustness, or if we want, the residual functionality of the system. And the robustness is related to the fragility estimates and repair rates that we discussed earlier. Also, we need to increase the availability or shorten the recovery time, and this is related to the recovery curves that we'll discuss next. The actual shape of a recovery curve is influenced by different factors, including the type and level of damage, availability of resources required for the repair, environmental conditions, and preparedness. Functions with different shapes have been used to model the recovery curves, where the choice of the function is typically based on a qualitative description of the situation. To model the recovery process in a more rigorous way, we develop a stochastic formulation that accounts for the actual work progress that needs to take place for the recovery. This is in contrast to assuming an arbitrary recovery curve. By modeling the state variable x during the recovery, we can estimate the capacity and demand, and then the reliability and functionality over time, accounting for the relevant uncertainties. We then combine this stochastic formulation for recovery with a state-dependent formulation for deterioration, which also models X, and I introduced it earlier, to perform a complete life cycle analysis using stochastic renewal theory. A common measure of resilience is related to the area under the recovery curve, often in the literature indicated with the letter R. However, R is only a partial descriptor of the recovery curve, and it is not sufficient to fully characterize it. Also, it does not provide any information about the spatial variability of the recovery process. So we propose new resilience metrics that are analogous to the already accepted metrics in probability theory. If we call Q the cumulative resilience function in analogy to the cumulative distribution function of a random variable, then we can introduce the center of resilience in analogy to the mean of a random variable and the resilience bandwidth in analogy to the standard deviation of a random variable. The definition of this matrix is completely general and can be systematically extended to higher order metrics, like higher order statistics, to now fully characterize the resilience associated with any recovery curve. As the individual components recover, the network's functionalities also recover. To model the regional recovery, we develop a multi-scale approach for interdependent infrastructure. The proposed approach partitions infrastructures into several recovery zones and prioritizes them based on the desired resilience objectives. The approach promotes recovery schedules that are feasible to implement and easy to manage and communicate. We extended the definition of resilience metrics to capture the spatial variability of the recovery. We defined a spatial center of resilience, ρ, to indicate the centroid of the recovery process at any given time. We also defined the spatial resilience bandwidth, chi, to indicate the spatial variability of the recovery around the spatial center of resilience. As an example, we modeled the recovery of the power network considering the actual priorities in a real post-disaster recovery. We estimated that after about 32 hours of repair work, all critical components have recovered. However, non-critical repairs may continue. We also modeled the recovery of the water network. A flow analysis of the water network with state variable x as a function of time, considering the reduced water capacity due to the power outage and the reduced water demand due to the population dislocation, allow us to assess the availability of water at any node over time. And we can see that immediately after an earthquake, the damaged network is unable to satisfy the minimum pressure requirements. However, after about 21 days of repair work, we have a full functional recovery. We also studied the recovery of mobility, healthcare accessibility, and police connectivity as a function of the transportation network recovery. We measured the recovery of mobility, healthcare access, and police connectivity in terms of the center of resilience that I introduced earlier. We also developed an optimization formulation to expedite the recovery of disrupted services while reducing the recovery cost. The formulation optimizes the resilience by developing rapid recovery schedules, and we implemented the formulation considering Shelby County, obtaining significant reductions in the recovery time. Next, let's talk about the recovery of business operations. We developed a physics-based formulation to model the recovery of business operations and predict the duration of business interruption. The formulation uses a combination of a multinomial logistic model and a random field model. The multinomial logistic model estimates the business owner attitude or class profile toward resuming business activities, while the random field predicts the duration of business interruption given interruption occurred and the predicted business owner class profile. The developed formulation is consistent with the formulation developed for physics-based fragility functions and repair rates that I introduced earlier in this presentation. Then we develop a mathematical formulation to model the impact of natural hazards on supply chains. We model the supply chains as a collection of networks, and then by modeling the dependencies of supply chain operations on physical structures and infrastructure, we cascade the effects of hazards. As an example, we model the interaction between the performance of the port in Miami-Dade and the cascading effect on the performance of businesses served by this port. And we quantify such interaction by estimating the changes in the business profit while accounting for the dependencies of business operations on the performance of the port. And finally, I'd like to talk about uncertainty quantification and model validation. We need to capture the effects of many random variables that enter a very complex computational workflow. Traditional approaches for uncertainty propagation are clearly not suitable. So we develop a novel formulation for the uncertainty propagation that is specific for regional risk and resilience analysis. The formulation allows us to quantify the uncertainty in the resilience measures and identify the main sources of uncertainty in the workflow. We develop a multi-level uncertainty propagation that breaks down the problem into several lower dimensional ones using the workflow hierarchy. We also develop different variable grouping schemes that reduce the number of simulations for each level and offer insights beyond the specific cases. Predictive models for risk and resilience analysis need to be calibrated and updated as data become available. So we collected data from the Mashiki town in Japan that was exposed to the 2016 Kumamoto earthquake. And we're now comparing the predictions from both existing and proposed models with the recorded data to validate the model predictions. We also develop a Bayesian updating for probabilistic multi-level models of interdependent infrastructure systems. The methodology allows us to update the model parameters in the lower level nested models in the complex computational workflow for regional risk and resilience analysis, considering different data types as they become available over the space and time. And the methodology can be used both after an event and for the real-time updating of the models and, of course, the predictions during the actual recovery. Finally, I'd like to make some concluding remarks. Regional risk and resilience analysis requires selecting the proper network granularity and model resolution. Requires capturing the spatial variability in the hazard and in the conditions of the structures and infrastructure. Requires accounting for the aging and deterioration of structures and infrastructure, which can have a significant impact on the vulnerability of the built environment and the recovery time. Requires modeling the dependencies and interdependencies among networks and systems to capture the loss or reduction in functionality of supporting critical infrastructure, in addition to the structural damage and the changes in demands on the systems. And finally, it requires ongoing validation and updating of the models using real field data. I presented a roadmap for regional risk and resilience analysis. I mentioned some specific models and formulation that we developed to address the above specific needs. The formulation is consistent in the different steps, general, and applicable to different regions and hazards. As we go forward, we need to incorporate the role of insurance in the models, since it can play an important role in redistributing and transferring risks and provide financial tools for the recovery. We need to consider the ability of individuals to adapt and recover independently from the recovery of the built infrastructure, and we need to pay more attention in quantifying the cost and benefits of mitigation strategies, urban planning, and public policies to find an optimal solution. Many articles on regional risk and resilience analysis can be found in the journal Reliability Engineering and System Safety. And as the editor-in-chief of the journal, I'd like to invite all of you to look at the papers in this journal, submit your own work, and possibly also submit proposal for special issues. I also want to bring to your attention 6 books that I have co-authored and that capture much of what I presented today.
Okay, thank you so much for the excellent presentation of Professor Gardoni from UIUC. So any attendances have any questions can ask Professor Gardoni. Yes. Yes, there is one question from Professor Dong, and the question is that in your modeling method, you consistently path from mechanical rules, modification path from lab data. Okay, my first question is about the generalizability of this model. Do you use real-time data from sensor to modify to your model when applying to different regions or different situations, such as focusing on fire, other disasters due to the climate change?
That's a question. Would you like me to answer the first one? Or do you want to go through the second one as well?
Yeah, first and second at the same time. Yes, thank you.
Okay, the second question is whether you could provide more insight when using networks to analyze physical damage and cyber damage. Okay, whether the different main challenges with these 2 classes of damages, and what is the challenge of jointly consider them using network analysis tools. Okay, these are great questions. And first of all, let me thank you one more time for the opportunity to give this presentation and entertain some question in this discussion. These are great questions. To tackle the first one, the idea of starting from a physical model and then expanding that physical model with data and calibrating probabilistic models that are really including everything we know. We have data and we have understanding of the physics or the mechanics of the problem. So really the goal is to use everything we have, not only the rules of physics and mechanics, not only the data. And in the literature, in everybody's work, sometimes we're tempted to use only the rules of physics and mechanics. And historically, that's what we used to do, right? A lot of the structural analysis, a lot of the mechanics models were based on the fundamental rules of physics, Newton and Euler and so on. Now, more recently, is actually quite fashionable. A lot of the paper I see are really data-driven. But we need to be a little careful with that because we don't always have a lot of data. And for civil engineering applications, for mechanical engineering applications, nuclear engineering, and there are many fields inside engineering where we actually don't have a lot of data. In the example I was talking about today, we're talking about natural hazard. We really don't have a lot of data, fortunately. Now, these are rare events. So we want to use the data because they tell us something. But we don't have enough data to have the luxury of ignoring the rules of physics and mechanics. So that's really the idea of bringing them together, everything. We're trying to include everything we have, to use all the information that are available. But that comes with an additional benefit. And that's what I'm getting at to the question and answering the question here. The additional benefit is that the rules of physics and mechanics are always valid. So even if we, for example, have a taller column or a wider diameter or different configurations, the rules of physics and mechanics will not change. It's not that we are suddenly on a different planet where there might be different rules of physics and mechanics. And so that means that, while in contrast to that, a purely data-driven model is only applicable within the range of the data. And the moment you go away from the data, even when you are within, but you are away from a data point, that might give you some errors. Like if you think about the Kriging models, like they're perfect at the points where you have the data, but they have an increasing error as you move away from these points. So by merging or combining all the information that we have, we're actually able to extend the applicability of the model, the generalizability of the model to other cases. Now, when we look at fires, for example, this was another question, or part of that question, fire or climate change. I didn't present it today, only had 45 minutes or so. I do have a separate presentation where I talk about in more details about the fragility functions. And we have developed fragility functions for other hazards, for vehicle impacts, for scour, for, I presented here bridges, we've done it for other structures as well. And now we also work at the fragility of building of fire following an earthquake, for example. So this is more related to the fire. And the idea is we're using the same framework, the same mathematical approach, combining the rules of physics with the data. But of course, when we have a different hazard, we need to have a new set of data. We need to have new physical models because it's a different physical problem. And so while we can use the same formulation, it would have to be, the model would have to be redeveloped for a different hazard. One example of that, we looked at vehicle, 18-wheeler, big trucks, hitting a column. And when they hit a column, even though it's a column, like the one I will show you earlier, and it's a shear failure maybe of the column, there is a rate effect due to the fact that it's a high velocity impact. So it's really a different problem. So the physics is different, the data need to be different, but we can use the same framework. And the second question was more related about the network. Now, specifically here, I was talking about physical network, water and power, but we are also been working, and it's a little bit behind the scene of what I presented here, we're talking about social networks. Because if you think about the demand on the system depends on how many people will be around, how many people will go to work, whether they will dislocate or not. So in that case, the network is not only physical, but we have a different network. And similarly, even though we have not done it, but similarly, one could think of other network of different types. So we have not done cyber, we have not done cyber damage, but I don't see why that would be necessarily different. There would be, for example, a control station or a control system. There would be in lack of functionality that is maybe induced by a cyber damage, and that would then propagate in the functionality of the overall system. So we have not done it, but I would say that conceptually it could be extended to these cases as well. So both great questions, and I think that's probably already spoke enough about this.
Yeah, Professor Gardoni, I have also had two questions for you. Okay,
Yeah,
the
please.
first question is that in Australia, so actually in 2019 and 2020, we had the huge bushfire. And just in the past few months, we had 100 years flood, and then most of the city in New South Wales and Victoria just this month, and a lot of I say house are destroyed. But the point is that actually we did not do much during the disaster. I say from the decision maker like the government and also the defense, we don't actually. So we only relied on the people to stay the house by themselves. But we did provide a lot of support after disaster, such as the government support, like you can apply for out to 70,000 for the reconstruction of your house. And also the insurance will cover some of that. I did see in your last slides, you present some insights for supporting that decision. So I would like to see how can you explain it a little bit more, like how can you define the support we should get to the people, and how the insurance, I say company, I say verify the claims from the insurance. Yes, so that is my first questions.
Yeah, that's a great question, and I'm answering maybe tangentially, maybe not at the heart of it. We can come back to that. I had several conversations with insurance and reinsurance companies, and in a way, we always, when we do research, I think a good question is, who is the audience? Who is going to use this stuff, right? Especially if we're talking about for engineers, and who is going to be using this? It's not intended to be for the library. We don't do work to put it in the library, I hope, right? So who could be the beneficiary of this information? So on one hand, communities could benefit for this kind of analysis, because in a way, what we're doing here is trying to predict what could happen in the future under different scenarios. Instead of waiting for something to happen and learn from the past experience, which is still a good thing, and that's what we have done for many years, what we're trying to do is almost have a tool here, a game, okay, it's almost like a video game, but instead of being made up, or a movie, but instead of being by Disney, is actual based on actual good predictions that would lay out and predict what could happen if there is a certain earthquake, or if there is a hurricane of a certain magnitude, or if there is a wildfire, for example. If we're doing a lot, I didn't include it here because some of it is more ongoing. So I thought, okay, let's just stay focused on things that are more complete and publishable. In the way, I was providing references throughout in the presentation, the way if somebody's interested, they can actually read it. Some of the work on wildfire that we're doing is still in progress, and so I didn't include it. But that's exactly what I presented here more for earthquakes. We're doing a very similar type of analysis for wildfires. And communities can benefit from that, because we can say, this is what we are expecting to happen. But also insurance companies and reinsurance companies. For insurance and reinsurance is tricky in a way, because accurate predictions might not be necessarily what they need. They need to figure out what is the right premium so that they're profitable. So a little bit of different goal than a mayor of a city or a governor of a state. I mean, if it was in the US, maybe in Australia, you have a different kind of political organization, but whoever is in charge of a city or of a region could benefit from this kind of information. And what is nice is if we only learn from the past, we really don't know, other than through a guess, what would be the benefit of doing something. But when we have a tool like this, allow us to run what-if scenario. And so we can see what would be the benefit of certain interventions. What would be the benefit of cutting down some trees, for example? What would be the benefit of building some barriers in case of a levee, in case of a hurricane, or of implementing different strategies? And we can have a good estimate of the cost, and we can now quantify with tools like this, we can quantify the benefits of these strategies. So that's really the goal and the audience, if you want, of this kind of work.
Yeah.
A little separately, I didn't present, I just mentioned in a bullet, we've done some work on cat bonds. And cat bonds is when basically a reinsurance company transfer the risk to the market, and the pricing on the cat bonds is tricky, and this can help in that way too, because we can have a prediction of what could be the losses. So I don't know whether I really answered your question, but I think it kind of was on this kind of general area.
Yes, thank you so much. Actually, I think your answer is quite useful, because for the policy makers and also for the insurance company, they want to see how much the disaster will cost to them and what the resource they should reserve for recovering, for the community to recovering from that disaster. So thank you
That's
so
correct.
much. The second question is about the computation times, because you see, in your analysis, and the system is a very large scale. So I just wondering how much time do we need in the analysis about the impact analysis, as well as possible mitigation strategy. So this is very interesting to our group, especially Associate Professor Don working on the reinforcement learning for large scale system, how to minimize the computational time.
Yeah, that's a great question. And so I want to divide two types of analysis here.
Yeah.
Okay? One is when we are running a scenario, and it is today, November 9, I want to run an hypothetical scenario for the future, for a possible future earthquake. And might happen next year, might happen 2 years from now, or even a future wildfire that is not happening right now, is in the future.
Yeah.
So in that case, computational time is not a deal breaker. You know, the overall time for a relatively large area, about 1 million people, is a few hours. The whole story, the whole analysis. Okay, but a few hours is not a problem. We have that time. Where we're trying to be more efficient is when the hazard is happening, is actually unfolding. Now, for earthquake, it doesn't matter. The earthquake, boom, happens, and you have the damage. It's a matter of seconds. But think about a hurricane. We know hours, several hours before landing, that the hurricane is forming and is gradually approaching. For a wildfire, you have a fire that started, and it's going to take some time for the fire to move and unfold the extent of damage they could have. So because the computational models are relatively fast, of course, one can make them faster, but they're fast enough. What we can do is a Bayesian updating of the predictions. So for example, for the hurricane, when the hurricane is 10 hours away from the coast, we can have a prediction.
Yes.
Then the hurricane is now 5 hours away from before landing, and we have some information, for example, on the storm surge due to the incoming hurricane. We can use that information to update the prediction and fine-tune the model. And so we can do the same thing for the wildfire. As the wildfire is propagating, we have a model that tells us in which direction it's going to go and how quickly it's going to go. I didn't have it into the presentation, okay, but we have it. But now, if we are a few hours into the evolution of the wildfire and the prediction was not exactly right, we can correct it and we can do a better prediction for the future. So in that sense, the model has to be pretty quick so that we can do this updating. Now, there is one part that is very time consuming and is the development of the capacity models, of the demand models. But those are done up front. The regional risk analysis is just calling these capacity models, calling these demand models, and very quickly doing a estimation of the probability of failure or of the damage, because we have a lot of pieces that are prepackaged in a way.
Yeah. Yeah, thank you so much for your answers. So now I have a better understanding about that, because sometimes, especially I say for the power system, so because we also do the optimal power flow, actually sometimes the computational time is very critical, because the power flow the yearning happen in half hour. If the computational time is larger than half hour, I say, oh, 15 minutes, it doesn't make any sense to such power flow planning. So thank you so much for your for your answers to my questions. And also, I just asked other audience, do you have any other questions for Professor Gardoni? Okay, if there is no more questions from the audience, let's say thank you to Professor Gardoni, and we can end today's seminar.
Thank you all again. Thank you for the opportunity to present this work. Thank you for the invitation. And on the very last slide, you can Google it otherwise, there was a YouTube channel where you can see other videos with a lot of the details. Some of them are actually addressing the question that we just talked about. So you can see more details there. But also invite all of you to send me an email if there's anything you want to talk about, or maybe even ideas for collaborations. This is a very exciting field. So if there are opportunities to collaborate, I'm always very keen on doing that. And send me an email and we'll do something together. Thank you all again for the invitation.
Thank you. Thank you. Bye. Have a nice day.
Bye. Thank you. Bye. You too.
Bye.